Hi there. So we're back, and what I'm going to do today is talk a little bit about angles. Okay. Now, what do I mean by talk about angles? Great question. What I'm talking about here is that, maybe you have a certain angle you find from a particular initial coordinate system. I should use this hand, initial coordinate system to the principal directions, right? And I've got students saying to me, well, you know, if I've got, you know, 12 degrees to get to my principal directions, do I use 12 degrees plus 45 to get to the shear or 12 degrees minus 45 to get to the shear? That's one thing that I've got students asking me. And again, as some of these things happen to turn out, they seem like a big deal. They really aren't. And I want to point out why that isn't a big deal. The second thing is we make this little assumption, right? And there's this assertion that I see all the time that says, oh, well, if sigma x minus sigma y is bigger than 0, then the x direction points to the bigger principal stress and all this stuff. And you never really see a satisfying proof of that. I'd much rather have a slightly more satisfying proof that, hey, this is why this works. So my setup here is I've got a stress block within the limits of me drawing a square with this thing here, right? It's not quite a square. We'll live with it. I've got sigma x and sigma y. I've got some axial stresses on there. I've also got two shear stresses drawn on there, which is unusual. And I've got them in different colors because the red I want to correspond to having a positive, counterclockwise couple on the x faces shear stress. And I want the purple to correspond to the negative clockwise couple on the x faces shear stress. I want both of them because I'm going to draw a bit of an unusual set of Mohr circles here in a few minutes. Yes, I said Mohr circle. If that frightens you, don't worry about it. We're not going to be doing any numbers with it. All we're going to be doing is doing what Mohr circle does best, and that is using it to show a concept. So remember, of course, we've got theta p equals 1/2 inverse tangent of tau xy over sigma x minus sigma y over 2. That's a basic equation. There's a video back from about a week ago from me. You can find something somewhere else, doesn't matter, that shows how this comes about. That's all good. So now what? I said that if sigma x minus sigma y is bigger than 0, then x goes to sigma p1 or sigma 1, y goes to sigma p2 or sigma 2, where we assume, of course, right, in general, what we're going to assume, I should probably note this, sigma 1 is bigger than sigma 2. Okay, this is an assumption. You don't have to order your principal stresses that way, but people will look at you funny if you don't. Okay, just make sure sigma 1 is bigger on a number line basis, mind you, not magnitude. -5 is smaller than +2, right? So remember, make sigma 1 bigger than sigma 2. That's what we're going to be doing throughout here. We're going to be ordering them in that way. So what I can do is I can set up something like a Mohr circle-esque thing. Notice how I'm not saying a Mohr circle because I'm not going to put a vertical axis on these. I don't want you to get stuck thinking that, oh, well, this is what happens if sigma 1 is bigger than 0 and sigma 2 is less than 0, or this is what happens if they're both bigger than 0. No, this is just what will happen no matter what the magnitudes are if sigma 1 is bigger than sigma 2. Okay, so if we've said that sigma 1 is bigger than sigma 2, we also have, I should scroll back up for a second, sigma x minus sigma y is bigger than 0, right? Well, that equation has a second consequence. I can rewrite that as sigma x is bigger than sigma y. Why did I just do that? What did that just get me? Well, remember, if I have the case with the counterclockwise couple on the x faces, right? The positive shear stress, as we call it, I plot the x point below the axis. Well, I know that sigma x is bigger than sigma y. That means that sigma x is also bigger than sigma average. Sigma x is sitting somewhere out here. My x point has to live over here because the x stress has to be bigger than the y stress. And this is what my Mohr circle looks like. And if I have a positive value in that principal angle equation, I'm going to have a positive tau in the numerator. Sigma x minus sigma y is bigger than 0. I've got a positive in the denominator. I've got a positive result. I've got a counterclockwise angle. That is where twice theta p lives for this instance. And notice how the x point through theta p rotates up to meet sigma 1. Hey, not so bad, right? But what if I have a negative shear stress, you may be saying? That can't be the same, can it? You're right and you're wrong at the same time. It's the same in that x will rotate to sigma 1. It's different in that it doesn't rotate the same way, right? So on the flattest part of my attempt at a Mohr circle freehand, again, compasses and tablets don't mix. These Mohr circles are going to be a little ratty, right? My x point must be here. Why? First of all, the x stress is bigger than the y normal stress. Therefore, the x stress must be to the right of the center of Mohr's circle, and the y stress must be to the left of the center of Mohr's circle. Now I've got the clockwise couple on the x faces, though. It's spinning clockwise, which is going to be this way, okay? So what that buys me is that I must plot my x point above the sigma axis, and therefore the y point goes below. And now, in this instance, well, you're saying, okay, well, 2 theta p, what's that going to buy me? Again, sigma x minus sigma y is bigger than 0. So the denominator of our principal angle equation, I should say, up here, I just scrolled it in, right? That denominator is positive, but my shear stress is negative, which means my angle is negative. My angle's clockwise all of a sudden. Hey, and if I go clockwise, I've got to do that. And no matter which way you look at it, whether you start off with a positive shear stress, the red line, or a negative shear stress, the purple, you wind up with the x point lying on top of sigma 1. Okay? I tried thinking of a way to describe this that wasn't hand-wavy, that didn't involve Mohr's circle, because full disclosure, I don't use Mohr's circle for much. It's good for this. It's real good for this. Okay? So that's one way to look at it. Okay, so that's if sigma x minus sigma y is bigger than 0. Great. What if sigma x minus sigma y is less than 0? We say, okay, well then x goes to sigma p2, and y goes to sigma p1. Y goes to the bigger principal stress, x goes to the smaller. Okay, so again, let's remember what this means. Sigma x minus sigma y is less than 0. Well, I can bring sigma y to the other side, and sigma x must be less than sigma y now. So my Mohr circles, yes, you may have seen this coming, right? Here we are again. Now, sigma x is less than sigma y. That means when I take the average, sigma x is also less than the average, right? It's got to be. Therefore, if I go with the positive shear stress again, right, I plot my x point with the positive, since it has a counterclockwise couple, I should say, I plot it below the axis. Again, I'm not locking down where the tau axis is. I don't want you to think this depends on the magnitudes of sigma 1 and sigma 2 compared to 0. It doesn't. So I'm trying to throw that right out. Yes, I know this looks strange for a Mohr circle. I admit that. But it works, right? So there's my x point, because x has to be to the left of the center. Less than is to the left, right? Here's my y point. Here's my diameter that connects the x and the y points. Okay, well, I have a positive shear stress. But sigma x minus sigma y, the denominator of that principal angle equation, is negative. I've got a negative angle, don't I? Because I've got positive in the numerator, negative in the denominator. I must have a clockwise rotation. And here's my clockwise rotation all of a sudden. Look at that. Look at x. It sits right on sigma 2 when we're done. And I think you're seeing it now. My x point, if my shear stress is negative, goes above the axis. My y point goes below the axis, below the sigma axis, if you will. And now, if I go and evaluate 2 theta p, or the inverse, basically the angle theta p, what I'm going to find is that my tangent function from the first page of this thing, right, I've got a negative in the denominator because sigma x minus sigma y was less than 0. I've got a negative in the numerator because tau xy is less than 0. I've got a positive angle counterclockwise. And let's watch that x point take a walk right down to sigma 2 one more time. Okay, so a thing to be careful of here, right, is I have no problem with people, if you're taking a class with me, I have no problem with you going online and checking your work with a Mohr circle calculator, or checking your work with MATLAB, or checking your work with a spreadsheet. Remember, notice I'm saying checking, okay, right? That doesn't mean doing it all. That means doing it by hand and saying, hey, how good was this anyway? Let me look at a tool to see if it's right. There are many Mohr circle tools out there. That's why I don't make my own, because it's a really crowded market, let's be honest, right? What am I going to add? People have done a pretty good job already, right? The thing is, they often like to make the x-axis be the one that points to the larger principal stress. That means you might get an angle that, let's say, if you've got plus 37 degrees in a situation like the purple on this circle, you might get minus 53 degrees out of an online calculator. Different number. What's going on? Remember that 37 minus negative 53 just happens to be 90. You've got a rotation that moves your x-axis 90 degrees from their x-axis. 90 degrees apart. Sounds like one of them is pointing to sigma 1, and one of them is pointing to sigma 2. That's all it is. Remember, the principal stresses live on perpendicular planes. If your angle and someone else's differ by 90 degrees, you've got the same setup. Just your x-axis is pointing to one principal stress and their x-axis is pointing to the other. No big deal. Speaking of no big deal, the other thing has to do with angle to shear planes. Okay, I got another page. What about magnitudes? What I like to do is I like to keep everything less than 45 degrees. That's just me. Makes life easy. Also means that we always have, if I can scroll up again just a second, we always have this acute angle, a less than 90 degree angle on Mohr's circle. Makes life easy, right? This way I can have something in mind. It keeps things straighter for me, right? But what people have asked me is, in a setup like this, I'm saying theta p happens to be 10 degrees for this setup. Why? Just because. It's 10 degrees. Roll with it, right? It can be any number we want. So what you can say from here is, if you want to find the angle to maximum shear, I can say that theta s equals theta p minus 45 degrees. And what I would get is a stress block down here. Down here with my new axial stresses, which we know are both equal to the average value, and my new shear stress, which I'm going to call tau sub p, not for principal, but for in-plane maximum shear stress, because as you may have seen, this isn't necessarily the 3D maximum, and the way I've drawn it, it actually isn't, right? So I can do that and get theta s equals theta p minus 45 degrees equals minus 35 degrees. And I get students who say to me, well, wait a minute. Why would I choose that angle? What about theta p plus 45 degrees? And something I didn't draw in on this figure that I'm going to now, I've got an S2 axis and an S1. Why S2 and S1? S1 is where the x-axis went to get to maximum shear, and S2 is where the y-axis went, right? Again, I'm using a number of 10 degrees for the principal angles. It works for anything. I just want to put a number in your head so this way I could draw something out. That's all. The only reason I've got a number there. Okay. What if I do plus 45 degrees? Well, I'm going to do this in terms of the axes, okay? What if I make that equal, let's say that is equal to theta s prime, just to give it a name, right? Which in this case would be equal to 55 degrees. All right, well, what I had to start off with was my XY coordinate system. I took it and I spun it down, right? And this is going to be S2, S1. And I spun it downward by 35 degrees. I probably shouldn't have the negative on there, right? This is 35 degrees, which we said was theta S. But I've got someone else who wants to go 55 degrees clockwise, counterclockwise. I've gone 35 degrees clockwise. Someone else wants to go 55 degrees counterclockwise. Okay, what does that do? Well, remember, this in the corner here, I'll use black, that's a right angle. So this angle here, I'll put an arrow on the green one as well, that angle is, of course, 90 degrees minus 35 degrees, and there's your 55 degree rotation. So if you were to decide to start off with X and Y, and I'm going to give away the game here, put a big old OR in there, right? You can decide to say, hey, I'm going to put my S1 here and my S2 here because I'm going by 55 degrees. And notice, the red S1 is on top of the black S2. And the red S2, yeah, it's negative the black S1, but they're the same direction, right? So whether you add or subtract those 45 degrees, you wind up with axes that are, here we go again, 90 degrees apart, which means they're the same stress block, okay? You get two rotations that are 90 degrees apart, you get to the same place. I never quite know when the webcam is going to cut me off, right? If I start here and I go 90 degrees, all I've done is I've swapped the X and Y stresses. That's it, right? And for the maximum shear block, who cares? The X and Y stress are the same anyhow because they're both equal to the average, right? So it doesn't really matter, okay? So what I'm trying to do with this, and hopefully what you're seeing out of this, is there are some things that look like important subtleties, which in reality we don't care, right? Ask a student who's had me in a class, one of the most common phrases I might come up with is, I don't care. Why? Because this distinction isn't that important, right? Sure, it's good to know whether you've rotated 35 degrees down or 55 degrees up. Fine. But you're going to get to the same orientation just with axes pointing in the different directions, and you're going to get the same stresses. If there were a feature, like some kind of crack or some kind of weld sitting at an angle, well then yeah, I really care about that angle now. For this, the angle doesn't really make a difference, because if you choose plus 55 and I choose minus 35, for this particular case, if we have a principal angle of 10 degrees, right, we both get the same maximum shear stress values, and we both wind up with the same orientation, just your axes and mine are spun by 90 degrees, and it doesn't matter, because they're really pointing along the same lines now, aren't they? Okay, so thanks for watching. Any questions? Let me know.